Let us solve design of truss problem. In this we have considered the problem. Just go through. In the question paper they usually provide a line diagram of a roof truss. Okay, so here also the question, that is line diagram of the roof truss and the member length, and that corresponding member is having the force and nature of the force is given. Okay, so let us go through the question once. A line diagram of a roof truss with internal force, loads and forces in each members are shown in the figure. So design various members of the roof truss along with their end connections with bolts, and also design the bearing plates at the supports for the reaction and anchor bolts for an uplift force of 15 kilonewton. So this is the information given. Okay, so with this information, before solving any truss design or truss design, we should follow certain steps. For that you need to remember these points, that is select double angle for top chord and bottom chord. See this one, A to D, A, B, C, D, D, E, F, G, this will be considered as top chord, and A, L, K, J, I, H, G, this will be considered as bottom chord. So for this top chord and bottom chord you need to select double angle section which will be available in the steel table. Okay, and this one what I am showing is considered as inner chord. Okay, for this inner members you can go with the single angle sections. So select the double angle for top chord and bottom chords, select single angle for inner chords, and provide minimum 2 bolts. Suppose if you want to fix this member, provide minimum of 2 bolts for the connection in if you go with the bolted connection. Okay, if you are going with the welded connection, no need to worry about the number of bolts, right? Same way, take effective length of that member as LE, which is equal to 0.85 times the actual length, by considering it is fixed. Next, provide uniform thickness of the gusset plate. If you want to fix this member, you need to provide one gusset plate, right? That gusset plate will be uniform throughout the section. And next, select minimum size of the angle as ISA 50 by 50 by 6 millimeter. For any angle, it might be inner chord or top chord or bottom chord, minimum angle size should be 50 by 50 by 6 millimeter. Okay, so with this let us solve the problem. So you need not to bother, so many members are there, how to design or what to do and all, you need not to worry. What you need to do is just identify at the top chord and bottom chord what is the nature of the force available, as well as you need to understand, suppose in the question negative sign or in the nature, instead of C and T, C represents compression and T represents tension. Instead of C and T, if they have provided positive and negative signs, you should be understanding position. Compression means negative sign and tension means positive sign. Okay, so what you need to understand here is, for the top chord, that is A, B, B, C, C, D, D, E, E, F and F, G. A, B, BC and FE, BC and FE are same. Next, CD and ED are same. So these are top chord. In this, what is the nature of the force given? Compression, compression, compression. So all this member is having compression natured force, right? So what you need to do? You need to select the highest of these three forces, that is 240, and design for the compression member. Okay, so if you do by selecting 240 kilonewton force and compression member, the whole top chord process or top chord design is over. You need not to design each and every member. Okay, if you are selecting highest of these three means 240, if you design for 240, obviously this will be coming within 240, right? So it will be resisted or design will be satisfied. So consider 240 out of these 6 members A, B, G, F, B, C, F, E, C, D, E, D. So out of 6 members, if you select 240 and go with the compression, that is enough. Okay, no need to worry about much members. Same way, if you consider bottom chord, A, L, LK, KJ, JI, IH and HG. Come here in the table. AL, same way HG or GH, next LK and HI, and next KJ and IJ. KJ and IJ. So this means, I think, see, these three will come into the bottom chord members, correct? Bottom chord members. So if you go with the nature of the force, this will belongs to tension. Again, this one is also tension. This is also tension. So what is the nature of the force? Tension. Bottom chord is having tension natured force. Now in these three force, what is the highest one? 207.84. So if you consider 207.84 and design as a tension member, the bottom chord step is over. Okay. So the next thing is inner chord member. So in the inner chord member, so all these are inner chord member, right? Because all these are inner chord. So let us go with the nature of the force. If you move on to the right side, okay, there is no force in the BL and FH, no, zero force is given, so no need to worry. Move on to CK and EI. So tension force is given for CK and EI. CK and EI, this is having tension, right? And next DJ is having compression. Same way the other one BK, FI, CJ, EJ are also compression, and this is tension. So what we need to do for the inner member or inner chord is we need to design for both tension as well as compression. For this 15 kilonewton, we should design as tension member, and out of this, by considering 66, we'll design as compression member. So wherever the nature, both natured force, both that is tension and compression force is given, instead of inner chord, if you get nature of force, compression and tension in the top chord also, you need to design for tension member and compression member both. In this problem for the top chord, we got only compression member or nature of force as compression, so we are going to design it as only compression. We are not going to design about tension. Okay, same way for the bottom chord, only tension force is given, so only tension design is enough. But for the inner member, both tension as well as compression both is provided, so we need to design that member, both tension member as well as compression member for the given force. Okay. So let us try to solve. Let us take the first one, that is top chord. Design of top chord. In design of top chord, how many members are there? AB, BC, CD, DE, EF and FG, correct. So out of this, what is the maximum force in the tabular column? That is, I am having here, for AB we are having 240 kilonewton and BC we are having 210 kilonewton and for CD we are having 160 kilonewton, correct. So same way the same force will be on the other members also. So now what is the highest force here? 240, right? And what is the nature of the force? Compression. So let us write among three forces 240 kilonewton is the highest force, correct. So let us solve or consider 240 kilonewton as the force. So factored load is equal to 1.5 into 240, which is equal to 360 kilonewton design top chord as compression member for 360 kilonewton. Design top chord as compression member for 360 kilonewton. So what is the procedure to do as compression member? You have studied in the previous semester, that is in the model compression member design. Okay. So now what is the clear span given? Span given is 2.3 meter. Let us assume FCD is equal to 110 Newton per mm square, 110 Newton per mm square. From page 34 IS 800, PD is equal to area into FCD. So what is PD? We just calculated, that is 360 into 10 cube, which is equal to AE into FCD. We just assume 110. So what would be the effective area? Effective area will be equal to, I have the value here, 3272.72 mm square. So effective area is this much. So which suits to this area, we should select double angle from the steel table, and minimum angle should be how much? 50 by 50 by 6. So let us go with the steel table and I'll consider from steel table select two ISA 90 by 10 millimeter. Select two ISA 90 by 90 by 10 millimeter. So effective area of this particular section will be 1703 mm square. So we are considering two angles. So 3406 will become, so what is the actual area? 3272. We should consider more than this area. So that is suitable. It is 3406 millimeter square. So once we found area, what is the next step? We need to write section properties for the selected section, that is ISA 90 by 90 by 10. What are the section properties? R minimum equals to 27.3 millimeter, effective area 3406 millimeter square. So what is the effective length? Effective length is equal to 0.85 into, what is the length we considered? 2.31 meter. So if you calculate, it will become 1.9635 meter. So what is slenderness ratio? KL by R. This is 1.9635 into 10 power 3 divided by R minimum is 27.3. So what is, if you solve this, 71.92 will be the value of lambda, that is slenderness ratio. By having this value, again we should go with the steel table, we should go with the IS 800 code book and get the FCD value. Page 42. For FY 250 Newton per mm square, for KL by R 70, FCD value is 152 Newton per mm square, and for 80 it is 136 Newton per mm square. For 70 it is 152. It is given in the, for the class C in the steel, that is IS 800, page number 42, for yield strength of 250. For KL by R value of 70, you will get 152 as the FCD value, and for the 80 you will get 136, but we want at 71.92. So if you do interpolation, you will get the actual value of FCD. That we'll do here. For 71.92, FCD will become 148.98 Newton per 148.928 Newton per mm square. So now let us put the value into the PD is equal to area into FCD formula. Effective area is how much we considered? 3406 into FCD is 148.928, which will give us PD as how much? 7.25 kilonewton will be coming. So this value is greater than 360 kilonewton, which we have considered or given in the question. After factor load, it will come 360 kilonewton, but the selected section, that is ISA 90 by 90 by 10 double angle, will be having design load resisting power as 507.2425 kilonewton. So obviously it is greater than the 360 kilonewton, so it is safe what we have selected. Hence safe. The next step is connection. Next is connection. Let us consider bolted connection. Bolted connection. For this, using M16 grade of 5.6 bolts. Okay. So now, what is die of the bolt? 16 mm. What D naught will become? 18 mm, that is clearance for the hole. And next, what is ultimate strength of the bolt? As we have considered grade 5.6, 500 Newton per mm square. What is the edge distance? Edge distance will be 1.5 times D naught, that is 1.5 into D naught is 18. And what is pitch distance? Would be 2.5 times D. So 2.5 into die of the bolt is 16 mm. So if you solve this, this will become 30 millimeter and this will become, it is actually a few, that is 410 Newton per mm. The next step is connection. In the connection, we need to check, as we all know, in the shear and as well as in the bearing. What is the bolt value in shear and what is the bolt value in bearing? So if you consider in shear, let us assume the failure of the bolt happens in the threads, not in the shank portion but in the thread portion. So what is the formula for the shear? VDSB is equal to 1 divided by gamma MB into NN multiplied by ANB plus NS multiplied by ASB. Whole thing multiplied by ultimate strength of the bolt divided by root 3. This is the formula which is readily available in the code book. So if you put the value, that is gamma MB is factor of safety 1.25, the available shear planes is 2 planes, and A and B is the net area of the bolt, that is A and B is equal to 0.78 into pi d square by 4. D is 16 mm. If you do so, 156.82 will be available and this will be considered as 0 because the bolt will failure at the threaded portion itself, not in the shank portion. So it will, if you solve this, as we have considered the 5.6 grade bolt, FUB will become 500. So VDSB or shear value of the bolt will be 72.43 kilonewton. Same way if you do in bearing capacity, so bearing capacity of the bolt will be VDPB, that is design bearing strength, is equal to nominal bearing strength to the factor of safety. So what is factor of safety? Here also same 1.25. VNPB, that is nominal bearing strength of the bolt, will be equal to 2.5 times KB D die of the bolt, T thickness of the plate or angle, and ultimate strength of the angle we should consider. So 2.5 KB will be least of these 4 values, that is KB edge distance divided by 3 times die of the hole, and second one is pitch distance divided by 3 times die of the hole minus 0.25, and ultimate strength of the bolt to the ultimate strength of the angle. If you do so, the first one will get 0.55 and the second one will get 0.49 and third one 1.21 and the last one is 1. Out of these 4, the least value is what? The least value is 0.49 and that is what we are going to consider least of the above, that is KB value will be 0.49. Now everything we got know in this equation. Let us put the 0.49 as KB value, and KB is how much? 0.49 and die of the bolt is 16 mm, thickness of the angle is 10 mm, FU, that is plate, is 410. If you solve this, you are going to get this value as 64.28 kilonewton as the bearing strength of the bolt. What is the shear strength of the bolt? We got 72.43 kilonewton. So out of shear and bearing, what is the strength of the bolt? Obviously the least of these two will be the strength of the bolt. So now the least of these two is 64.28, that is bolt will failure in the bearing than the shear value. So let us consider the bolt value as 64.28 kilonewton. So now what is the next step? How many number of bolts do we require to satisfy the load? So what is the load coming? I'll write here. Number of bolts required is total factored load divided by bolt value. So what is the factored load? 360 kilonewton, right? 360 kilonewton. What is the bolt value? 64.28 into 10 power 3. If you solve this, we are going to get number of bolts 5.6. 5.6, let it be 6 numbers of bolts required to 360 kilonewton load. Okay. So with this, the top chord design is over. That is only compression member, compression natured force was there. So the top chord, for the highest load we have designed. The next thing, let us consider the bottom chord, only tension load is there. So let us start the tension member design for the bottom chord. So the next step is design of bottom chord. Same. So out of these three, the highest force is 207.84 kilonewton. Correct. So for this 207.84, we need to design. So before designing, let us factor this 207.84 force. That is 207.84 multiplied by 1.5 will give us 311.76 kilonewton. So for this force, we need to design the member as tension member. So initially let us consider the rupture strength of this section. For tension member, we need to consider this rupture strength. Okay. So for the rupture strength, in the page number 33 of IS 800, you are having this formula, that is TDN is equal to alpha AN FU by gamma M1. This alpha will be depends on the number of bolts we are going to fix. Initially we have assumed that minimum number of bolts will be 2 for any connection. So on that basis, 2 number of bolts, alpha value will be 0.6. So TDN is nothing but what is the force we got. Okay, we are substituting this force to find out the area. Okay, once we got the area, we can able to select the section from the steel table. So for that, this load we have considered for TDN, that is design tension load, and next alpha is 0.6, net area we don't know, we need to find. Fu is the ultimate strength of the angle or plate 410, and factor of safety 1.25. So if you solve this, we are going to get AN as 1584.14 mm square. So on this basis, let us increase the value as per the code of this area 30 to 50%. Now let us increase the minimum value, that is 30% of this value will give us 2059.38 mm square. Next, to satisfy the area or based on the area, let us select one angle, that is 2 ISA 80 by 80 by 6 millimeter. Okay, and by considering this angle, what is the next step? The next step is to connection. Connection means we need to assume what is the dia of the bolt or grade of the bolt we are going to provide. As it is a tension member, let us assume HSFG bolt, that is high strength friction grip bolts of grade 5.6 M20 dia and 5.6 grade. And page number 76, if you look at, you will get this formula for HSFG bolt shear strength. Now gamma mf is the factor of safety, you know that, and mu f will be depends on the plastic section, that is 0.55 value which is available in the code book, and ne is the number of shear planes, as the gusset plate and two angles will be there. There will be two shear planes will come. And next is kh, that is available in the code book itself, that is 1. And f naught you need to find out. F naught is nothing but a and b into small f naught. Small f naught is nothing but 0.7 times the ultimate strength of the bolt. This is nothing but FUB. As we have assumed 5.6 grade, FUB will be 500. So 0.7 times 500 will give us F naught. So A and B is nothing but 0.78 pi d square by 4. Dia of the bolt 20 mm we have assumed. So if you solve this, we are going to get F naught as 85764. So let us put this value into the equation. So all the value we found, if you put all the values into the equation, that is VDSF, we are going to get it as 75.47 kilonewton. So once we got the strength of the bolt, what is the next step? We need to find what is the number of bolts required. Correct. So how to calculate the number of bolts? Number of bolts is equal to factored load divided by bolt value. Factored load is how much? 311.76 into 10 power 3 Newton, and bolt value is 75.47 into 10 power 3 Newton, and number of bolts required is 4.13. Let us round it off to 5 number of bolts required to fix the tension member. Okay, so how we will place the number of bolts, that is 5 numbers. I'll write it here. So now we were about to check for rupture. So check for rupture formula is TDN is equal to 0.9 ANC FU by gamma M1 plus beta AG naught FU by gamma M naught, which is available in the code book directly. The formula you need not to worry in the tension member. Okay. So now to understand this, you need to understand what is ANC or AG naught, how to calculate the connected legs net area and outstanding legs gross area. Okay, before going into the formula, you need to understand we have calculated 5 number of bolts, right? So in the angle that is 80 by 80 by 6, we have placed at a edge distance of 40 mm and at a pitch distance of 60 mm, we have placed 5 bolts. Okay, so in this, from the edge of the plate to the center of the first bolt is called as edge distance, we all know that. So same way, from center to center distance of the bolt is called as pitch distance, but from the starting bolt to the end bolt center to center distance is called as LC or length of the connection as 240 millimeter. And why do we need all these means? Here the value beta, to calculate beta, again there is one more formula, that is 1.4 minus 0.076 W by T and Fy by Fu, Bs by Lc. So these terms, that is W, Bs and Lc, to get it is very important to understand how you have placed the bolts in the angles. So here this is LC, that is length of the connection, 240. How this 240 came? Pitch distance is 60, 60 plus 60 plus 60 plus 60, 4 times it is equal to 240. Same way, length in the shear lane, that is from this bolt to the edge of the plate. For this 240, another 40 is added, so length will become 280 millimeter. Same way, in the transverse direction is called as LT. LT is 40 millimeter because LT from center of the bolt to the edge distance of the plate in the transverse direction. LV is in the direction of the shear, that is bolts parallel to the plate. Same way, LT is perpendicular to the LV direction. Okay, that is 40. D we considered as 20 millimeter and D naught is 22, that is die of the hole considering 2 mm clearance. LT is from this center to the edge of the plate, that is angle is 40. Why it is 40? Because total we have considered 80, in that we place the bolt at 40, so remaining distance from here to here is 40 is LT. W1 is 40, W1 is nothing but, see, from here where we have placed the bolt, I just told you at the center we have placed the bolt. So W1, this figure is available in the code book itself, you can find it. So same way, next is W. W is nothing but the whole thing 80, that is from here to here. I have written here W, from here to here it is 80 total. And next LV. LV means what? I just told you 280 millimeter, that is in the shear lane total length. And LC is the 240 millimeter length of the connection. And P is the pitch distance, E is the edge distance. With the help of this, how to calculate BS? BS we needed here, BS, a formula. So BS is equal to W plus W1 minus thickness of the angle. So W is 80, we just got to know, and W1 is 40 where the bolt is placed, and minus thickness of the plate we considered 80 by 80 by 6 millimeter. The least thickness is 6 millimeter. If you do so, BS will be available as 114 millimeter. So move on to the formula. So in this formula, beta is the unknown thing. To calculate beta, this is the formula. Here W we just calculated, that is 80 millimeter. T is thickness of the plate, 6 millimeter. Fy is yield strength, that is 250. Fu is the angle's ultimate strength, not bolts. So Fu is 410, and Bs we just calculated 114, and LC is the length of the connection 240, which should be less than or equal to FUB, that is ultimate strength of the bolt to the factor of safety, divided by yield strength to the factor of safety. It is 410 into 1.1 divided by 250 into 1.25, should be greater than or equal to 0.7. If you solve this, every data we got, if you put the available information into this equation, 1.4 minus 0.076, if you solve this, we are going to get the value as 1.1065, less than or equal to 1.44, that is this term, and greater than or equal to 0.7. Yes, it is satisfied, right? So we can consider if I rounded off this value to 1.11, so final beta value will be 1.11 I can use here. So the next unknown is connected areas, net connected legs, net area. So for this ANC is equal to A, that is direction total 80 member, 80 length, minus D naught is the hole minus thickness by 2. In that hole, what is the area we are going to deduct? D naught is the 18 width and thickness is also how much? 6 millimeter. So if we deduct that multiplied by the thickness will give us connected areas neck 330 mm square. And next, gross areas is how much? In gross area we need not to deduct the whole dia, or where we are going to insert the bolt, that hole we need not to deduct. So breadth is 80 millimeter. This is also breadth only, don't confuse. I just written A. So 80, okay, instead of A I will write it here B only, so that it will not be confused. So thickness by 2, 6 divided by 2 multiplied by 6 will give us how much? Why it is thickness by 2? Because this angle is not uniform throughout the length, right? It is not uniform, or we are concentrated in this direction. Okay. So here we want to calculate, in that line we want to calculate the area. So 80 minus 6 divided by 2 into thickness will give us gross area. In the gross area, if you deduct D naught, see everything is same, B minus T2, B minus T by 2 into T. Only the addition here is the dia of the hole. The dia of the hole we are deducting from the gross area. So these two values just substitute here. Here we are going to get TDN. What is TDN? That is rupture value. What is rupture value? Just I'll erase this and write. So all the information we got, with the help of this information, TDN is equal to the same formula. ANC we just calculated, that is 330, 410 by 1.25 ultimate to factor of safety, plus beta value 1.11 into 426 is the gross area into 250 by 1.1. If you solve this, you are going to get 213.96 kilonewton. Because it is a double angle, we have nowhere multiplied with the number 2 value. So I am multiplying it here at the end. So initially don't confuse with the area. I have considered for only one angle. Now I am multiplying that force into 2. So actual resisting force in the rupture is 427.92. What is the actual force coming? That is factored load is 311.76 kilonewton, right, as per the given condition. So the resisting force in the rupture is how much? 427.92. So this is greater than 311.76. So it is safe in the rupture condition. The ultimate or last condition is block shear failure. So let us check the block shear failure. So the next step is block shear failure. Under block shear failure, this is the formula which is available in the page number 33 of IS 800. TDB1 is equal to AVG Fy root 3 gamma m naught plus 0.9 HEN Fu by gamma m1, and also So you can use any two, but least of this value will be considered for the design. So TDB2 is 0.9 AVN FU root 3 gamma M1 plus ATG FY gamma M0. If you observe this formula, see Fy root 3 gamma M0 or 0.9 Fu gamma M1 Fy gamma M0, all this instead of AVN, ATG, ATN and AVG, only these four things are unknown in this equation, right? So if you find these four things, you can easily solve this equation, correct? So how to get these four things? AVG means gross area in the shear direction, net area transverse to the shear direction. This is gross area transverse into the shear direction. This is net area in shear direction. Shear direction means along the bolt. Okay. So now, how to calculate this? Let us go one by one. That is, we know that number of bolts is 5 bolts. Just imagine or go back to the previous step and observe the 5 bolts what we have placed in the angle. Okay. So LV is 280 millimeter. What is LV in the shear direction? From the edge distance to the last bolt center distance is total 6. And next for LC it was 240, length of the connection from outermost bolts center to center distance was 240. So AVG is nothing but shear plane's gross area is nothing but length of the shear multiplied by thickness. So LV is 280 multiplied by thickness of the plate is 6. If you multiply this, you will get AVG as 1680 millimeter square. Next ATN. ATN is nothing but gross area of transverse direction minus 0.5 times, because if you consider that angle bolt will be here, we want from this center to this area, correct, this distance. So we are going to deduct this portion, half of the bolts, and this portion only we are deducting, that is 0.5 thickness of that angle multiplied by the hole. Okay, only half of the bolt we are deducting. And what is ATG? ATG, that is transverse direction gross area, that is nothing but LT. This is 40, right? Out of 80 we have placed bolt at 40 from the center to the edge distance. So 40 multiplied by the thickness of the plate will give us transverse directions area, that is gross area. In the gross area we are going to deduct the half of the hole, that is 0.5 T D0. So ATN, that is transverse direction net area, will be 174 mm square. So AVG is over, ATN is over, and ATG also over gross area. The last step is AVN, that is shear line's net area in the shear lane. So AVG minus, AVG is gross area minus number of bolts and half of it. Okay. So into thickness of the plate multiplied by the hole dia. So AVG we have already calculated, that is 1680 gross area. In gross area 5 number of bolts are there. Under 5 number of bolts minus 0.5 into thickness of the plate is 6, D0 is 22, we got AVN also. So all these 4 areas we calculated, just substitute that into the equation. AVG is 1680, Fy is 250 divided by root 3 gamma M0, root 3 gamma M0 value 1.1 plus 0.9 ATN. ATN we calculated 174 mm square, 174 into Fu 410 gamma M1 1.25. With that we got TDB1 as 271.8 kilonewton. Same way the next step TDB2
0.9 AVN. AVN we calculated 1086. 0.91086 into FU, that is 410, divided by root 3 into gamma M1 is 1.25, plus ATG. ATG is how much? 240 is what? 240 here, multiplied by 250 divided by 1, that is nothing but Fy to gamma M0. If you solve that, you will get 239. So least of these two is 239, because we need to consider double angle. So 239 into 2 will give us 479.2 kilonewton carrying capacity. What is the actual load we have considered for tension? That is 311.76 after factoring. So 479 is greater than 311, hence in this case also, that is in the block shear failure also, the section is safe. So bottom chord is also safe with what we have considered, that is 80 by 80 by 6 millimeter angle, which is to be placed with the 5 number of bolts, is satisfied for the bottom chord. The next step is inner chord member design. For that inner chord, I told you only one section, that is single angle will be considered, not the double angle. Fine.